This is a video reviewing stoichiometry, which is basically calculating the amount of substances given a chemical equation. So those substances could be reactants, they could be products. The unit could be in moles, molecules, mass, really anything. So stoichiometry is something that you are actually familiar with, even if you don't really realize it. So in our everyday life, we use stoichiometry, especially I like to think when baking. So consider when you have a bonfire with your family in a COVID-free scenario. Maybe you are having family over and you are going to grill out hot dogs with a bonfire. To make a hot dog, you need one hot dog and one hot dog bun to make your hot dog bun complex. It's kind of like a combination reaction. So this is the chemical equation or recipe for making a hot dog. When you go to the store, you get one pack of hot dogs, which includes 8 dogs. Since there's a 1-to-1 ratio for hot dog to hot dog bun complex, you can make 8 hot dogs from this pack. You also grab a pack of hot dog buns. This comes in a 10 pack, 10 buns, not 10 bund, sorry, a little typo there. And again, since it's a 1-to-1 ratio, you know that with your 10 buns, you could make up to 10 hot dogs. Now you know that you only have 8 actual hot dogs, so you know that you're limited by the 8 hot dogs. That's called a limiting reactant, which we will get to later. But that stoichiometry, predicting the amount of product we can make, given the reactants that we get in the store, is exactly stoichiometry. You can consider the same thing when you're like baking cookies or something. So maybe you want to double a recipe. When you double a recipe, you're basically using stoichiometry for that recipe to double your yield. Another example would be like making s'mores, and not everything here is a 1-to-1 ratio, so it's a little bit more complex. So one s'more, you're going to have 2 graham cracker squares, 1 marshmallow, and then 3 of those small Hershey rectangles. So I represent the graham cracker as G2 because 1 graham cracker rectangle contains 2 graham squares. So that's just an example of like a diatomic element in s'mores. Plus a marshmallow and then plus 3 chocolate rectangles would give you your s'more, which is G2MC3. If you're given an entire Hershey's bar, which contains 12 of those little rectangles, how many s'mores could you make? With this recipe, we know, okay, we have 12 chocolate rectangles. There's 1 s'more for every 3 chocolate rectangles. If we do 12 times 1 divided by 3, we find out that we can make up to 4 s'mores with 1 Hershey bar. And this setup here is what we call dimensional analysis. So it has units, which is basically the identity of those, and then we basically cancel out to find G2MC3. If you would want to make 10 s'mores, how many G2s would you need? For this one, you're starting, you say, okay, 10 s'mores, that's 10 G2MC3. There's 1 G2 per every 1 G2MC3. I get that from the coefficients in the balanced chemical equation. And I find out that I need 10 G2s, which is 10 rectangles of graham cracker. So when we actually apply these to actual balanced chemical equations, not food recipes, we usually are referring to mole ratios. So food is an example of a macroscopic object that we can easily count individual pieces of. You can easily count 1 marshmallow out. But since atoms and molecules are very small, they're microscopic, we typically measure these in a larger quantity that's called a mole. And a mole is kind of like a dozen. So 1 dozen eggs is 12 eggs. 1 mole of anything, so 1 mole eggs, would be equal to 6.02 times 10 to the 23 eggs. So it's a very large number, and that just makes it measurable in our little macroscopic world, since we can't exactly measure out 1 atom of oxygen or 1 atom of nitrogen or anything like that. So for example, for producing water, a chemist can't simply reach into a container, get 1 atom, or really molecule, of O2 and 2 molecules of H2 to make 2 molecules of water. In the lab, those scales and things simply aren't that sensitive, nor can we just simply get one little atom. The chemist can measure 1 mole of oxygen and 1 mole or 2 moles of H2 to make 2 moles of water. And usually scientists will use molar mass to actually measure this on the scale. So molar mass, hopefully you remember, you get from the periodic table. So the molar mass of oxygen, which is just O, would be 16 grams per mole. For O2, it would be 32 grams of O2 in 1 mole of O2. So chemical equations, you can think about them in many different ways. So the way that we begin to think about them when we first introduce them is usually on an atomic or molecular level. So we can say that we have 1 molecule of N2 and 3 molecules of H2 to produce 2 molecules of NH3. And that's what this diagram is kind of representing. But again, in the lab, scientists can't measure out just 1 molecule or 1 atom. So usually they are adding 1 mole of N2 plus 3 moles of H2 to get 2 moles of NH3. This process specifically is just the production of ammonia, NH3. Now scales and things, they don't read out number of moles. What they give us is grams. So we could also use the molar mass to express this equation in grams. But since, 1 gram of hydrogen is not going to be the same as a gram of carbon, like you're not going to have the same number of atoms or molecules, usually that's why the chemical equation is expressed in molar ratios or molecular ratios. But chemists can do math using molar mass to figure out what the mass of those things are to actually measure them out for a chemical reaction. So mole ratios are determined from a balanced chemical equation and used to produce the moles of reactants or products given a known mole of one substance. So for example, if we're given a known amount of H2, the conversion factor or mole ratio that I would use to determine how much nitrogen I would need to use all of that hydrogen would be 1 mole of N2 per every 3 moles of H2. And the reason I choose that one is because of dimensional analysis. So my known is H2 and my unknown is N2. Basically, I want my unknown to be in the numerator and this to be in the denominator so that my units kind of cancel out here. But if we are given N2 and want to know H2, I could easily say that there are 3 moles of H2 for every 1 mole of N2. So basically every reactant and every product has a relationship with one another that we can express as a mole ratio given the coefficients that are given in a balanced chemical equation. So here we're given an example where we are given moles of something and we want to find moles of something else. So how many moles of N2 is needed to produce 12 moles of NH3? 12 moles of NH3 is our known, so that's where I'm going to start. My unknown is how many moles of N2. So I'm going to say that given my balanced chemical equation, I have 1 mole of N2 per every 2 moles of NH3. So if I take that, my moles of NH3 will cancel out. I'm left with moles of N2. 12 times 1 is 12, divided by 2 is 6. So 6 moles of N2 are needed. You can also go mole to mass. So with this, we're going to be starting with moles of product, 12 moles of NH3, to figure out how many moles of reactant we're going to need, to then go to mass. So in a chemical equation, we are pretty much always using a mole-to-mole ratio because, again, we can directly compare moles. We can't necessarily directly compare masses. So if we are basically comparing 2 different species in a chemical equation, we're going to be using a mole-to-mole ratio. Then once we have the moles of what we're interested in, we can do a last conversion into grams. So here I'm going to start with my 12 moles of NH3, go to moles of N2 by multiplying by my mole ratio, and then go to grams of N2 by multiplying by molar mass. So on the periodic table, the molar mass of nitrogen, N, is 14.01. So the molar mass of N2, which is 2 nitrogens, would be 2 times 14.01, which is 28.02 grams in 1 mole. So again, my moles of NH3 cancel out. Then my moles of N2 cancel out, and I'm left with grams of N2. I would need 168.12 grams of N2 to produce 12 moles of NH3. You can also go the other way if you're given mass of something, you want to know moles. So here, I want to produce 12 grams of NH3. I want to know how many moles of N2 I need. So I will go mass of products to moles of product, then moles of reactant. Because again, to compare things in a chemical equation, we have to have things in terms of moles. So that first one, going 12 grams of NH3 to moles, I'm going to have to divide by molar mass. And if you use dimensional analysis, you can clearly see why. I want my unit, gram, to cancel out, and I want to be left with moles. So I get 12 grams of NH3 divided by 17.034 grams of NH3. So that is, again, the molar mass of nitrogen plus the molar mass of 3 hydrogen. And that's in 1 mole. So then I'm left with moles of NH3. And then I can use my molar ratio to figure out how many moles of N2 that would be, which again comes from the balanced chemical equation. And I know that I would need 0.35 moles of N2 to produce 12 grams of NH3. We can also do mass to mass. So again, what mass of N2 would be needed to produce 12 grams of NH3? For this, I'm going to go the mass of my product to the moles of my product, to the moles of my reactant, to the mass of my reactant. Okay, so again, comparing products and reactants, I have to use moles, and in the beginning and end, that's where I start with mass. So I'm going to again go from 12 grams of NH3, divided by grams of NH3 gives me moles of NH3. Use molar ratio to go to N2, and then multiply by molar mass to get grams of N2. So my units will cancel. Grams here, moles here, and I'm left with grams. So I would need 9.87 grams of N2 to produce 12 grams of NH3. Okay, so that's an example of stoichiometry using just mass and moles. I'm also going to do a video that brings in volume to this comparison as well. But when you think of stoichiometry, I always like to think of baking or cooking in the kitchen. You're basically altering a recipe given what you have to predict how much you will get in the end. Okay, please let me know if you have any questions.